Welcome back to literal equations. Literal equations that require factoring. Up to this point, when we have solved literal equations, we have not needed to factor. That is because there was only one of the variable for which we were solving. For example, the problem we just did, a equals p plus prt, I asked you to solve for t, and there was only one t. However, if I asked you to solve this exact same equation for p, we see there are two p's. That means to solve for p, we will need to factor. So there's the whole key to recognizing when I will need to factor and when I will not. If in this equation I'm solving for r or for t, there's only one of them, I do not need to factor. When I need to solve for p, I notice there are two of them. That tells me I need to factor. All right, so let's take this equation and solve it for p. Oops. Well, I kind of gave away the first step. The first step is we're going to factor. We notice we have two p's. The p is in common, so we factor out the p. When I factor out the p, I have 1 plus rt left over. I have the 1 because what if I were to distribute, p times 1 would give me the p times rt would give me the prt. Pretty easy to forget that 1. Now, I notice the p is connected by a multiply, so I do a divide. My answer is p equals a over 1 plus rt. Now, I want to point out a very common mistake that students make. This is going to be wrong, and I'll talk about why it's wrong. A lot of students would say, well, I'm just going to take this and I'm going to subtract PRT on both sides and write A minus PRT equals P. And say, hey, I'm done. I solved for P. I have P all by itself over here. Well, when we say solve for P, we mean have P all by itself over here, have a bunch of variables over here, but not the letter P over here. So this is not solved for P, even though P is all by itself. It's not solved for P because there's a P over here. Okay? So again, the big key is there is more than one P. Since there is more than one P, that tells you you're going to need to factor. So let's look at a few more of these. Solve A equals mgh plus 1/2 mv squared for m. And this happens to be the formula for energy of a falling object. You don't need to know that. I just gave it to you. I don't know why I used A and not E. I should have used E for energy. Anyway, the key is I'm trying to solve for m, and I notice there are two m's. Since I see there are two m's, that tells me I need to factor. So I'm going to write A equals, I'm going to factor out the common m, and what's left over is gh plus 1/2 v squared. And now I notice the m is connected only by a multiply. So to get the m all by itself, I do a divide. I'm dividing by kind of a big ugly thing, but that's okay. It's one division. So my answer is m equals a over gh plus 1/2 v squared. Again, something I want to point out, if I asked you to solve for g, you would not have to factor because there's only one g in this formula. The reason we had to factor is because we were solving for m and there were multiple m's. All right, we got two more problems to do here. A equals 2LW plus 2LH plus 2HW. We're going to solve for h. This happens to be the formula for surface area of a box. Again, you didn't need to know that. I just kind of wanted to show you that I'm not just making up silly little formulas here. These are actually something used in real life. All right, now I noticed that I have two h's, one there and one there. So I know I'm going to need to factor. What I'd really like to do is take out the GCF on the right hand side, but I notice there isn't one because this one does not have an h in it. That's not a problem. If you're trying to solve for h and you see there are two h's, what you want to do first is get all the pieces with h on one side, all the pieces without h on the other. In other words, our first step in this problem is to subtract the 2LW on both sides. So we're going to write A minus 2LW equals 2LH plus 2HW. Alright, so I'm trying to solve for H. Basically, I want to get all the things that have H on one side, all the things that do not have H on the other. So I did that by subtracting the 2LW. Now, I'm trying to solve for H. Two things with H. Now I'm going to factor. A minus 2LW equals, now my GCF is really 2H, but I don't care about the 2 in this case. I'm trying to solve for H. So we're going to factor, but we're not going to factor out the greatest common factor. We're just going to take out a common factor. I'm only going to take out the H. It really wouldn't be wrong to take out the 2L, take out the 2 also, I mean. It's just really not needed. I'm trying to solve for H. I might as well only take out the H. Because now to solve for the H, I divide by this thing. So my final answer is H equals A minus 2LW divided by 2L plus 2W. Alright, so that one was a bit more complicated. Quick review. We noticed we had two H's. First step was to get everything with H on one side, everything without H on the other. The reason we want everything with H on one side is so we can factor the H out. Once we factor the H out, we do a division. Alright, our last problem. By far the most complicated. 1 over big R equals 1 over R sub 1 plus 1 over R sub 2. I find that these little numbers tend to bother people. You should be used to dealing with these little numbers, though. It doesn't bother you if I use little numbers in a formula like this. M equals Y sub 2 minus Y sub 1. You know this means the second Y number, and this means the first Y number. Same thing's happening here. What this formula says is, if I have two resistance items in a circuit, resistance number 1 and resistance number 2, the total resistance R is related to R1 and R2 by this formula. 1 over R equals 1 over R1 plus 1 over R2. That's a famous formula from electricity. Again, you don't really need to know where that comes from. I'm just trying to point out that it's not some crazy fake thing that I made up. Now, what I would do with this problem is I see a bunch of fractions. When I see fractions in an equation, I almost always get rid of them. To get rid of them, I need a common denominator. A common denominator has to have an R, an R1, and an R2. And remember, these are all three different things. This means the first resistance. This means the second resistance. Those are two different things. And this is all the resistance together. All right, so I'm going to multiply by the common denominator. The common denominator needs an R, an R1, and an R2. And I have to do that everywhere. And then look what happens. Here I have an R on top, and here I have an R on bottom. Those R's go away. I'm left with R1, R2. Equals. Over here I have an R1 on top and an R1 on bottom. Those go away. I'm left with R, R2. And then finally this one, I have an R2 on top, an R2 on bottom. Those reduce out. I'm left with R, R1. So there's my first step. My first step to make things a lot easier is, let's get rid of all the fractions. Now, I'm trying to solve for R1. I notice there's an R1 there, and there's an R1 there. There's more than one R1. If you're trying to solve, and there's more than one of them, you need to get them on the same side. So, I'm going to do R1, R2, and I'm going to subtract R1 on both sides. I subtract the R1 so that I have both the R1s on one side and no R1s over on this side. Again, the reason I do that is it allows me to factor. I now have a common factor of R1 right here. When I take the R1 out, I'm left with R2 minus R equals R2. And finally, to get the R1 all by itself, I can divide. Which means my final answer is R1 equals RR2 divided by R2 minus R. Alright, as I said, that was a very complicated one. Very complicated because it has these subscript things. Those usually confuse people at first. And then I had all these different looking fractions. But again, a good step, anytime you see an equation with a fraction in it, an excellent first step is to multiply everything by the common denominator and make all the fractions go away.